There is a direct relationship between the temperature and the vapor pressure. As the temperature increases, the vapor pressure of a liquid will also increase. The mathematical relationship between temperature and vapor pressure is known as the Clausius-Clapeyron equation. It says that the natural log of the vapor pressure is equal to negative enthalpy of vaporization divided by the gas constant R times 1 over temperature plus C, which is just some constant. This is written in the form of y equals mx plus b, where y is our ln of vapor pressure, x is our 1 over temperature, and the slope m is negative delta H over R. P is the vapor pressure, and it can be in any units of pressure: millimeters of mercury, atmospheres, torr, pascals. Delta H of vaporization represents the heat of vaporization. This could be in units of joules per mole or kilojoules per mole. R is the gas constant that we saw before, except for it has different units so that it cancels with the enthalpy of vaporization. We previously saw 0.0821 liters times atmospheres over moles times Kelvin. This gas constant is written in the units of joules over Kelvin times moles. So it converted liter atmosphere, which is actually another unit for work, to joules. We will use 8.314 joules per Kelvin times mole, or 8.314 times 10 to the negative third kilojoules per Kelvin times mole. Temperature has to be absolute temperature scale, so it has to be converted to units of Kelvin. And C is a constant that would depend upon the substance itself. Typically, this form of the Clausius-Clapeyron equation is only used if we're graphing. So if we went into the lab and actually collected some data on the vapor pressure and temperatures of a liquid, we could plot them using Excel. And from the slope, we could determine an unknown enthalpy of vaporization. Delta H of vaporization will change depending upon the intermolecular forces within the substance. A higher enthalpy of vaporization represents something that has stronger intermolecular forces. A lower enthalpy of vaporization represents a substance that has weaker intermolecular forces, and it's easier to vaporize it or convert it from the liquid state into the gaseous state. Since that form of the Clausius-Clapeyron equation was written in the y equals mx plus b form, if we were to graph the natural log of the vapor pressure on the y-axis and 1 over temperature in units of Kelvin on the x-axis, we would end up with a straight line with a negative slope. The slope, or m of our line, would be equal to negative delta H of vaporization over R, the gas constant. Usually this is used if we're solving for the enthalpy of vaporization of a substance. A more commonly used form of the Clausius-Clapeyron equation is a derived two-point version, which allows us to solve for an unknown vapor pressure or an unknown temperature, or if we know the vapor pressure and the temperature at two conditions, we can find the unknown enthalpy of vaporization of the substance. This says that the natural log of the vapor pressure 2 equals the natural log of the vapor pressure 1 plus the enthalpy of vaporization divided by R, that gas law constant. Units will be 8.314 joules per Kelvin times moles times 1 over T1 minus 1 over T2, assuring that both of our temperatures are in units of Kelvin. Our pressure can still be in any units of pressure. The vapor pressure of ethanol at 34.7 degrees C is 100 millimeters of mercury, and the heat of vaporization of ethanol is 38.6 kilojoules per mole. What is the vapor pressure of ethanol in millimeters of mercury at 65 degrees Celsius? We know at 34.7 degrees Celsius, the vapor pressure is 100 millimeters of mercury. We're trying to figure out what the vapor pressure is at a higher temperature, at 65 degrees Celsius. Since there's a direct relationship between temperature and vapor pressure, we should expect a vapor pressure that is greater than 100 millimeters of mercury. Let's assign T1 as being 34.7 degrees Celsius, and then we're going to need to add 273 in order to convert it to units of Kelvin. so that'll be 308 Kelvin. P1 will go with T1, and so that will be 100 millimeters of mercury. T2, our second temperature, is 65 degrees Celsius. Converting that to units of Kelvin will give us 338 Kelvin. And P sub 2 is what we're trying to find. When we calculate it, it will also be in units of millimeters of mercury, since that's what we plugged in for P sub 1. We were also given the enthalpy of vaporization, 38.6 kilojoules per mole. This is our delta H sub vape. That's how much energy is required to convert ethanol from the liquid state to the gaseous state. R, our gas constant, can be written as 8.314 times 10 to the negative third kilojoules per mole Kelvin. We want R to be in kilojoules per mole, so it cancels with the enthalpy of vaporization, which is also given to us in kilojoules per mole. The other alternative would have been to convert delta H into joules per mole first. Using the Clausius-Clapeyron equation, ln of P sub 2 equals ln of P sub 1 plus delta H of vaporization divided by R times 1 over T1 minus 1 over T2. We can plug in what we know so far. ln of P2 will equal the natural log of P1, which is 100 millimeters of mercury, plus our enthalpy of vaporization was 38.6 kilojoules per mole, divided by the gas constant, 8.314, times 10 to the negative third kilojoules over moles times Kelvin, times 1 over T1. T1 was our 308 Kelvin, minus 1 over T2, which was 338 Kelvin. If we check our units, we can see that kilojoules will cancel, moles will cancel, Kelvin cancels, and we're left with millimeters of mercury, which is what we want since we're calculating a new pressure. The ln of P2 should come out to equaling 5.956. We have to undo the natural log, so if we take e to the ln of P2 on the left-hand side of the equation, we'll take e to the 5.956 on the right-hand side of the equation. E will undo the natural log function. That will give us P2 equals 386 millimeters of mercury. Ether has a vapor pressure of 400 millimeters of mercury at 17.9 degrees Celsius and a normal boiling point of 34.6 degrees Celsius. What is the enthalpy of vaporization for ether in kilojoules per mole? So we know the vapor pressure is 400 millimeters of mercury at a given temperature, about 18 degrees Celsius. So if we call T1 17.9 degrees Celsius and convert that into units of Kelvin, that'll give us 291 Kelvin. P1 is the pressure associated with that temperature then, which is 400 millimeters of mercury. If we're going to calculate the enthalpy of vaporization, delta H sub vape, we need to know T2 and P2 as well. By them telling us the normal boiling point of 34.6 degrees Celsius, we can figure out what T2 and P2 are. Normal boiling point is the boiling point that's measured at 1 atmosphere pressure, which is 760 millimeters of mercury. So our T2 is going to be 34.6 degrees Celsius. Converting that into Kelvin, that's approximately 308 Kelvin. And our pressure will be 760 millimeters of mercury, so we keep it the same as P sub 1. Now we can rearrange the Clausius-Clapeyron equation in order to solve for the unknown vapor pressure. So starting with ln of P2 equals ln of P1 plus delta H of vaporization over R times 1 over T1 minus 1 over T2. We want to isolate delta H of vaporization over R, so we can subtract ln of P1 from both sides of the equation. So we'll have ln of P2 minus ln of P1. And we can also divide by the whole term 1 over T1 minus 1 over T2. That will give us that side of the equation equal to delta H of vaporization over R. The last thing we'll have to do is multiply both sides of the equation by R. That'll cancel it from the denominator here. We'll write that in parentheses and we'll multiply by R. So that means our heat of vaporization is equal to, and we can rewrite ln of P2 minus ln of P1 as the ln of P2 divided by P1 to simplify it a little bit more, times R divided by 1 over T1 minus 1 over T2. Now we'll go ahead and plug in everything. Natural log of P2, which we assigned as 760 millimeters of mercury, divided by P1, which is 400 millimeters of mercury, times R, which is 8.314, times 10 to the negative third kilojoules per mole times Kelvin, divided by 1 over T1. T1 is 291 Kelvin, minus 1 over T2, which is 308 Kelvin. Our enthalpy of vaporization should already be in units of kilojoules per mole at this point when we calculate it, which should end up coming out to 28.6 kilojoules per mole. And remember that that number tells you essentially how easy or how hard it is to convert your liquid from a liquid state to the gaseous state, or vaporize it, which is what the name of that phase change is. The stronger the IMFs, the higher the enthalpy of vaporization will be. So ether, which is a shorthand name for something called diethyl ether, looks something like this. It has some carbon and hydrogen bonds, but it also is polar due to the shape around the oxygen, which is bonded to two carbons. So it ends up having dipole-dipole interactions, which are not as strong as hydrogen bonding, but it will be a little bit stronger than something that ended up just having London dispersion forces. Let's review the phase changes, sometimes referred to as state of matter changes, and talk about them in relation to the intermolecular forces now. Going from the solid state to the liquid state is called melting or fusion. Going from the liquid state to the gaseous state is referred to as vaporization. And substances that can go from the gas state back to the solid state is called deposition. If we look at this going in reverse then, going from the gaseous state back to the liquid state is referred to as condensation. Going from the liquid state to the solid state is called freezing. And substances that can go directly from a solid to the gas state is called sublimation. As we go from a solid to a liquid to a gas, we have to break the intermolecular forces of attraction between the substances. We're not changing the intramolecular forces. So imagine we have water that's starting out as ice, and then it's melting, going to a liquid, and then it's vaporizing, going to steam or gaseous water. In between each of those phase changes, water remains water. It's still two hydrogens bonded to an oxygen, but we have to break the hydrogen bonding that exists between the water molecules. This is going to require energy input. Therefore, all of those phase changes going from solid to liquid or liquid to gas will be endothermic processes. The exact opposite will be true as we go from a gas to a liquid and condense it, or we go from a liquid to a solid and have freezing. In this case, we are forming new intermolecular forces. Going from a gas to a liquid, gases don't have really any intermolecular forces between them because the particles are spaced out so far. So we have to form some of those intermolecular forces when water becomes in the liquid state. The true is also when we go from a liquid to a solid because now we're forming even more intermolecular forces between the particles. All of these processes will release energy from the system to the surroundings. They are all exothermic processes. Recall that an endothermic process has a delta H that is positive, where an exothermic process has a delta H that is negative. We will look at the enthalpy of phase changes, or how much energy is required to undergo certain state changes. The heat of vaporization, also known as the enthalpy of vaporization, is used to talk about the amount of energy that's required to convert a liquid into the vapor state at a constant temperature. In this case, it would be the boiling point if we're going from a liquid to a gas. The heat of fusion, or enthalpy of fusion, is the amount of energy required to convert a solid into a liquid at a constant temperature. This constant temperature would be the melting point. Let's look at some actual values associated with these phase changes. So for water, going from solid ice to liquid water, or melting or fusion, the delta H of fusion will be positive 6.01 kilojoules per mole, or positive 333 joules per gram. Some textbooks will report both values. Usually when we're solving problems, I find it's easier to start with the units in joules per gram. You will be given both. Going from liquid water to gaseous steam, once again, this is an endothermic process, so our heat of vaporization will be a positive value. It requires 40.65 kilojoules per mole in order to undergo this process for water, or positive 2,257 joules per gram. Looking at the reverse, going back from gaseous steam to liquid water, this is going to be an exothermic phenomenon, so energy will be released in this process. The enthalpy of condensation is exactly the same as the enthalpy of vaporization, but it's opposite in sign. So it'll be negative 40.65 kilojoules per mole, or negative 2,257 joules per gram to go backwards. Going from liquid water to solid ice or freezing, this is going to be the exact same as the enthalpy of fusion, but it'll be opposite in sign since it's an exothermic process. So delta H of freezing equals negative 6.01 kilojoules per mole, or negative 333 joules per gram. All of these values reported are only good for water. If we're doing a problem and the substance is not water, we would have to look up what the heats of vaporization or fusion or condensation or freezing are for that particular substance. In order to discuss and study these energy changes that are associated with phase changes, let's first begin by talking about how the temperature of a substance will vary as it is heated. So what happens to the temperature of a block of ice when you put a Bunsen burner underneath it? So imagine that we have a brick of ice here, and we're going to heat it up, and we're going to think about what happens a little at a time as the temperature below it is increased. Let's make a graph of temperature on the y-axis versus time on the x-axis, so we can visualize the temperature and the state changes that our block of ice will undergo. This is going to be called the heating curve, and we're visualizing it for water right now. So we have time on the x-axis, and we have temperature on the y-axis, and will be in degrees Celsius. Some important pieces of information are the freezing point or the melting point of water is equal to 0 degrees Celsius. The boiling point of water is equal to 100 degrees Celsius. So starting with our block of ice, let's imagine that our ice is at negative 10 degrees Celsius. As we begin warming up our block of ice, the temperature is going to increase. The temperature is going to increase until it reaches the melting point of water. So we just said that the melting point is 0 degrees Celsius. At this point, we have solid water at 0 degrees Celsius. Any energy that we keep inputting into the system is going to be used to convert our solid into a liquid. After a certain amount of energy is gained, we will have liquid water, but it will still be at 0 degrees Celsius. Let's imagine that we keep heating up our liquid water now. The energy that we add to the system is going to be put into increasing the temperature. It's going to keep increasing until it reaches water's boiling point, which is 100 degrees Celsius. At that point, we will have liquid water that will be at 100 degrees C. Any energy that we keep putting into the system will be used to vaporize or convert our liquid water into gaseous water, still at 100 degrees Celsius. If we keep heating it up, we can keep warming up our gas to some temperature. Let's just say maybe we keep heating it to 115 degrees Celsius. In theory, we could keep heating it higher and higher and higher. There are 5 regions that are important along this heating curve. If you recall, lowercase q is the symbol used to describe heat. So we'll call the first diagonal line Q1, the first horizontal line Q2, the second diagonal line Q3, the next horizontal line Q4, and the last diagonal line Q5. The diagonal lines Q1, Q3, and Q5 all represent temperature changes. We're not changing what state the substance is in along the diagonal lines. We're only changing the temperature at those points. Q2 and Q4 represent phase changes. Along those points, we're having a transition from one state to another. At Q2, we went from the solid state to the liquid state, and at Q4, we went from the liquid state to the gaseous state. Going from a liquid to a gas has a longer line right here because it requires much more energy to completely vaporize a substance. You have to completely break the intermolecular forces going from the liquid state to the gaseous state. So typically, enthalpies of vaporization will be much higher than enthalpies of fusion or melting. Our goal is to be able to calculate the energy changes associated with not just temperature changes like we did in Chapter 5 previously, but adding in now the energy changes associated with changing states of matter as well. On the next slide, we'll talk about how we can calculate those temperature changes and those phase changes. To calculate a change in temperature, we can use an equation that we've seen before. Q equals mc delta T, where m was the mass, lowercase c was the specific heat of the substance, and delta T was T final minus T initial. For water, there are different specific heats depending upon what state of matter water is in. Ice has a specific heat of 2.108 joules per gram degree Celsius. Water in its liquid state has a specific heat of 4.184 joules per gram degree Celsius. This is the one that we would have used in Chapter 5. Water in its gaseous state, or steam, has a specific heat of 1.996 joules per gram degree Celsius. When we use Q equals mc delta T, we'd be calculating a change in temperature along any of those diagonal lines on our heating curve. To calculate the energy associated with a state change or a change in phase, we'll use Q equals m times delta H, where m is the same mass as it is in the previous equation, and delta H is either the enthalpy of fusion, enthalpy of vaporization, enthalpy of condensation, etc., whatever phase change we're undergoing. Those values were given to us on a previous slide. For a heating curve, at most we could have 5 regions that our substance goes through. We saw that region 1 was the energy required just to warm the solid up. And then for water, since that was its melting point from 0 degrees Celsius, we could have solid water melting to liquid water in region 2. Fusion would be taking place. Region 3, we warmed our liquid water up from 0 degrees Celsius to 100 degrees Celsius. Then we had gaseous water at 100 degrees Celsius that was formed after vaporization took place. And then we were warming our gas up higher and higher and higher in temperature. In this case, when we calculate the energy, it's going to be a positive value because all of the processes here are endothermic, meaning they require energy. If we flip this graph around, we can look at a cooling curve for water. So now imagine that we're starting with a gas and we're cooling it all the way down to a solid. In this case, all of the processes are exothermic, and therefore if we calculate the heat associated with all of these processes, it'll be a negative value. So in region 1, we're starting with a gas, and first diagonal line is cooling the gas down. Then we have gaseous steam at 100 degrees Celsius. The next energy that we remove will take our gas and condense it into a liquid at 100 degrees Celsius. Then in region 3, we're cooling our liquid all the way down to its freezing point. For water, the freezing point is at 0 degrees Celsius, so we have liquid water at 0 degrees C. And then any more energy that's released will take the liquid water and freeze it into a solid, which is region 4. And then region 5, we're just cooling down our solid. In theory, we could cool it down to whatever temperature that's below the freezing point. How much heat in kilojoules is required to raise the temperature of 20 grams of water from 5 degrees Celsius to its boiling point and then completely vaporize it? So our freezing point of water is equal to 0 degrees Celsius, and our boiling point of water is equal to 100 degrees Celsius. Let's draw a heating curve to represent what's taking place. We're starting with our water at 5 degrees Celsius. And on our x-axis, this is just time. So since we are already above the freezing point of water, if it's at 5 degrees Celsius, it's starting out in its liquid state. Any energy that we put into the system is just simply going to go into warming up the liquid water. It's going to keep warming up until it reaches its boiling point, or 100 degrees Celsius. At its boiling point, it'll undergo a phase transition if we add more energy, and that will be used to convert it from the liquid state into the gaseous state. So in this example, we have region 1, which is our first diagonal line. We'll call that Q1. And we have region 2, which is our second line, which is our horizontal one that represents a state change. We'll call that one Q2. To calculate the total energy required for this process, that'll be Q total equals Q sub 1 plus Q sub 2. Q sub 1 is just a temperature change, so we can use MC delta T. M will be the mass. We have 20 grams. C is going to be the specific heat for liquid water, so C sub liquid, 4.184 joules per gram degrees Celsius, times delta T, which is T final minus T initial. Our final temperature was 100 minus our initial temperature, which was 5 degrees Celsius. Our grams will cancel, our degrees C will cancel, and we'll be left in units of joules. Q1 is equal to 7.95 times 10 to the third joules. It's okay to get a really large number because a joule is actually a rather small unit of energy. Q sub 2, or our phase change going from a liquid to a gas, will be equal to M times the delta H of vaporization in this case. The mass is still 20 grams. Delta H of vaporization for water going from a liquid to a gas is equal to 2,257 joules per gram. Our grams will cancel, and Q2 is equal to 4.51 times 10 to the fourth joules. To calculate the total energy required to change our liquid water from 5 degrees Celsius to gaseous steam at 100 degrees Celsius, we simply add Q1 and Q2 together. So Q total will be equal to 5.31 times 10 to the fourth joules, which equals 53.1 kilojoules. Determine the amount of energy in kilojoules required to heat 30 grams of ice from 0 degrees Celsius to 115 degrees Celsius. So we're starting with ice, so we're starting with water in its solid state. The melting point for water is 0 degrees Celsius. The boiling point for water is 100 degrees Celsius. Let's draw a heating curve. We're starting at 0 degrees Celsius already, so we're already at its melting point. We have solid ice that we're starting with, so the first thing it's going to have to do is undergo a phase transition from the solid state into the liquid state. Any energy that we add after that is going to go into warming up the liquid. It's going to warm until it reaches 100 degrees Celsius. At that, we've reached the boiling point, so it'll undergo a phase transition, this time from the liquid state to the gaseous state. And then we're told we're warming it to 115 degrees Celsius. So next, the energy will be used to heat up the gaseous steam. We have 4 regions, Q1, Q2, Q3, and Q4 to consider in this example. The total energy, or Q total, will be equal to the sum of the regions. So Q1 plus Q2 plus Q3 plus Q4. Q1 and Q3 are both phase changes in this example. Q2 and Q4 are temperature changes. Starting with Q1, Q1 will be equal to M delta H of fusion. So the mass of our ice is 30 grams times the heat of fusion for solid water, which is 333 joules per gram. That gives us for Q1 9.99 times 10 to the positive third joules. Just as last time, we'll see that our grams will cancel. Q2 is a temperature change. We have liquid water that's at 0 degrees Celsius going from liquid water to 100 degrees Celsius. So we're going to use Q equals MC delta T. The mass hasn't changed, it's still 30 grams. C, we're going to use the specific heat for liquid water, so C sub L. That is 4.184 joules per gram degrees Celsius times T final minus T initial. So we're going to have T final be 100 minus 0. So delta T will end up just being 100 degrees Celsius. Our grams will cancel, our degrees Celsius will cancel. We'll end up with units of joules. Q sub 2 should give you 1.255 times 10 to the fourth joules. Q3, region Q3 is another phase change. Now we're going from a liquid to a gas, so we're vaporizing. Q3 will be equal to M times delta H of vaporization. The mass is 30 grams. The heat of vaporization for water is 2,257 joules per gram. Our grams will cancel. Q3 will be equal to 6.77 times 10 to the fourth joules of energy. Lastly, Q4 is a temperature change. We're just warming up gas. We have starting gas at 100 degrees Celsius, and we're taking it to gas at 115 degrees Celsius. So we have a delta T. We're going to use MC delta T, but the specific heat we use will have to be for the gaseous state for water. Our mass is 30 grams. The specific heat for gaseous water is 1.996 joules per gram degrees Celsius times delta T, which will be final minus initial, 115 minus 100 degrees Celsius. Grams cancel, degrees C cancel, and our energy in joules for region Q4 should be 8.98 times 10 to the 2 joules. The energy associated with all four regions of our heating curve, or Q total, will be the sum of Q1, Q2, Q3, and Q4, which should come out to being 9.12 times 10 to the 4th joules, or 91.2 kilojoules. It's a positive value because everything was an endothermic process. Determine the amount of energy released when 25 grams of water at 75 degrees Celsius is cooled to ice at -5 degrees Celsius. In this case, since energy is being released, that means that the energy we calculate will be a negative value because it is an exothermic process. We're starting with water at 75 degrees Celsius, which means it must be in its liquid state because it's in between the melting point and the boiling point for water. The melting point or freezing point, which is the same thing, is at 0 degrees Celsius. This time we're going to draw a cooling curve. So we have our temperature on the y-axis and time on the x. We're starting with our liquid water at 75 degrees Celsius. If we remove energy, we're going to keep removing it until it falls down to its freezing point, which is at 0 degrees Celsius. Then any more energy removed will take water from its freezing point as a liquid to a solid. So we undergo a phase change. And then if we cool it down even more, we can cool it down to -5 degrees Celsius. We have three regions on our cooling curve, Q1, Q2, and Q3. Q2 represents our phase change from a liquid to a solid where it's undergoing freezing. Q1 and Q3 both represent temperature changes. Q total will equal the sum of Q1 plus Q2 plus Q3. Calculating the energy that's associated with lowering the temperature of water from 75 to 0 degrees Celsius is going to be Q1. So we started at 75, and then finally we had liquid water still at 0 degrees Celsius. So we'll use MC delta T to calculate the energy change. Our mass of water is 25 grams. Our C is the specific heat for liquid water because that's our state. So 4.184 joules per gram degrees Celsius. Our temperature change, T final minus T initial. Final was 0 degrees Celsius minus our initial, which was 75 degrees Celsius. This is where the negative will be introduced. Grams cancel, degrees Celsius cancels. Q1 is equal to -7.85 times 10 to the 3rd joules. Q2, this is going to be associated with the freezing phase change. We have liquid water at 0 degrees Celsius, and we're changing it to solid water still at 0 degrees Celsius, so no temperature change here. We're going to use M delta H of freezing. The mass is 25 grams, that never changes. The delta H of freezing is going to be the same as the delta H of fusion, which is melting, but it will be the opposite sign. So that'll be -333 joules per gram. Our units of grams will cancel, and Q2 comes out to being -8.33 times 10 to the 3rd joules. Q3 is the energy that's associated with cooling down our solid ice from 0 degrees Celsius to -5 degrees Celsius. So we have a temperature change. We're on a diagonal line. we will use MC delta T. We have to use the specific heat for solid water at this point. Our mass is 25 grams. Our C for solid water will be 2.108 joules per gram degrees Celsius, times our delta T, T final minus T initial. T final was -5 degrees Celsius minus 0 degrees Celsius, which was our T initial. Grams cancel, degrees C cancel. For Q3, we get -2.64 times 10 to the second joules. The total energy associated with this change we'll get from adding up Q1 plus Q2 plus Q3, and we get -1.64 times 10 to the third joules, which equals -16.4 kilojoules.